Today we're going to continue our lesson on temperature and thermal energy. We'd like you to be able to distinguish heat from thermal energy, explain what specific heat is and how to calculate heat transfer, and then understand an application of conservation of energy to heat transfers and calculate the temperature changes due to that. So hopefully, if you look, you can take a minute to compare and contrast conduction, convection, and radiation. That would be your bell ringer. Make sure you understand the difference in those three. I'll let you pause and do that quick. So, section 12.1, heat and thermal energy. Heat is different from thermal energy, and it's different from temperature. Heat is actually a type of energy. It's the energy that flows as a result of a difference in temperature. The symbol for heat will be Q when we get to our equations. And as is true of all energies, the units for heat will be joules in the SI system. Specific heat is different. This is the actual amount of energy it takes to raise the temperature of a unit mass by exactly one temperature unit. Usually, it's the amount of energy in joules needed to raise 1 gram of a substance 1 degree Celsius. Some books have it in terms of the amount of energy to raise 1 kilogram by 1 degree Celsius, or 1 Kelvin. So you need to be careful and check the units, but it's always joules divided by some temperature unit and some mass unit. For example, water has a specific heat of 4,180 joules per kilogram Celsius degree. In chemistry, we learned this number as 4.184, but that was in joules per gram Celsius degree. So it really is the same thing, it's just how much energy for a kilogram. So what that really means is, if I have exactly 1 kilogram of water, it would require 4,180 joules to raise the temperature by 1 Celsius degree. Or, if I have 1 kilogram of water at 10 degrees and I want it to go to 11 degrees, it takes 4,180 joules. If I have 1 kilogram of water at 80 degrees and I want to go to 81 degrees, it still takes 4,180 joules of energy to raise that. This is a property of materials, and it's different for every one. Water has one of the highest specific heats. Copper, on the other hand, has a specific heat of only 385 joules per kilogram Celsius degree. Now, you won't have to memorize these numbers. They will be given to you in a table. Your book has that on page 279. And what this means is, the energy required to raise 1 kilogram of water by a Celsius degree would actually raise 1 kilogram of copper 11 degrees. It doesn't take near as much energy to heat up copper as it does water. 4180 is roughly 11 times larger than 385. Now we can put this in equation form to actually calculate the amount of heat being transferred. And this will be one you'll want to put on your equation card. Q is the symbol, like we said, for heat energy. M is mass, measured in kilograms. C is the symbol for specific heat. Be careful not to confuse that with Celsius, the units for temperature. And delta T is the change in temperature. And that can either be in Kelvin or Celsius. It doesn't matter, because the change from Celsius to Kelvin is identical. And if we check the units, mass is kilograms, specific heat is joules over kilogram Celsius degrees, temperature is Celsius degrees. You'll notice what happens is the kilograms cancel out, Celsius degrees cancel out, and we're left with joules for Q, and that's what we measure energy in joules. So the units all work out. If you'd open your book to page 280, we'll do one example problem with that. And just look at question number 5 on page 280. The question says, how much heat is absorbed by 60 grams of copper when it goes from 20 to 80 degrees Celsius? Well, I'm going to use the same equation. In this case, I'm solving for heat, which is Q. My mass in the problem was 60 grams, which is really 0.060 kilograms. The specific heat of copper we gave you right up here, 385, or you could have looked it up in your book, 385 joules per kilogram Celsius degree. And my change in temperature went from 80 or 20 to 80 or 60 degrees is how much the temperature changed. So when you go ahead and multiply that together, 0.060 times 385 times 60, you end up getting 1386, which with 3 significant digits is 1390 joules. The thing students have to be careful of is make sure you keep Q, heat, separate from C, specific heat. That'll be a mistake some students make occasionally. Now let's look at calorimetry, or how we measure specific heat. We talked about this a little last year in chemistry as well. A calorimeter is simply a device used to measure changes in thermal energy. And we will show you one of these in class. We'll demonstrate what a calorimeter looks like. A cheap version of a calorimeter would simply be a styrofoam cup, but more expensive ones have a cup inside of another cup, so you have the insulation of the styrofoam plus air, a way to stick a thermometer in there and such. And it really works due to the conservation of energy in closed, isolated systems. So we're assuming heat is being trapped within that calorimeter. And if that's the case, then EA plus EB equals 0. E standing for energy. The energy of one system plus the energy of another has to equal 0 if it's conserved. So imagine you've got a calorimeter here full of water at 20 degrees Celsius. And if you add to that a block of metal at 60 degrees Celsius, what's going to happen is the metal will lose some of its heat energy to the water, so its temperature will go down. The water will gain heat, so its temperature will go up. Eventually, at some point, they're going to reach equilibrium. They'll both be at the same temperature, somewhere between 20 and 60. And that depends on how much metal and how much water you have and their specific heats. So the question, if you have two blocks of different temperatures stuck together, what's going to be the final temperature eventually? So maybe you have a block of lead next to a block of silver. They're touching. The heat's going to go from one way to the other. Well, we know the conservation of energy is conserved, and in this case the energy is heat energy. So the energy of the first block, A, can be found by using the Q equation, which would be mass of block A times specific heat of block A times the temperature change of block A. And if you add that to the heat energy of block B, which is mass of B, specific heat of B, temperature change of block B, the total change in energy has to be 0. Expanding this out, we get MACA. Change in temperature we know is always final minus initial. So final minus the temperature of A initial plus MBCB. Change in temperature B will also be final temperature minus temperature of B initial. That has to equal 0. I'm now going to distribute this, multiply this by everything in the parentheses, MACATF minus MACATA initial plus MBCBTF minus MBCBTB initial equals 0. Collecting like terms, in this case the like terms are the ones that have my final temperatures in them. I'm going to put those together, so here I have TF times MACA plus MBCB equaling, and I'm going to move the other term to the other side, MACATA initial plus MBCBTB initial. I can now divide both sides by the MACA plus MBCB term and get this equation. This is a way to calculate the final temperature of two systems in contact with each other. Either two blocks of metal just touching or two things in a calorimeter. But now you won't have to derive that yourself. Final temperature equals mass of the first block, specific heat of the first block, initial temperature of the first block, plus MBCB initial temperature of the second block, divided by MACA plus MBCB. And again, I would put that on your card because you really don't want to have to derive that on your own. So let's try an example of what this looks like. If I have half a kilogram of water at 15 degrees, and I put that in a calorimeter, and then I add 0.04 kilograms of zinc at 115 degrees, what's the final temperature? Well, without doing it, I know the temperature will be between 15 and 115. And I have a lot more water, so I would assume it would be closer to the 15. And zinc's specific heat is a lot less than water, so it doesn't carry as much energy in it. So hopefully my answer is somewhere down at the 15 degree or close to that original. So let's try this. I'm just going to use the equation I have up top to find my final temperature. And I'm going to let A stand for the water. So the mass of the water is 0.5 kilograms times the specific heat of water is 4180 joules per kilogram Celsius degree times the initial temperature of the water, 15 degrees. And you'll notice everything cancels out nice for me. Plus the mass of the other zinc, 0.040 kilograms. Now we need to look up zinc's specific heat, and that's found on page 279. It looks like it's 388 joules per kilogram Celsius degree, and its initial temperature was 115 Celsius degrees. So again, everything cancels out. We're left with joules there, divided by the first mass, which was 0.50, times its specific heat, 4180 joules per kilogram Celsius degree. Make sure you multiply those together, plus the second one, 0.040 kilograms times its specific heat, 388 joules per kilogram Celsius degree. Kilograms cancel out here, kilograms cancel out there. I now have joules on the top divided by joules over Celsius, so they're going to cancel out here, and I'm left with degrees Celsius. So multiply the first term, and I'll do this in steps for you. When I multiply the first three, I get 31350 plus 1784.8 divided by the first term turns out to be 2090 plus 15.52 add the top divided by the sum of the denominator, and we get a final temperature of 15.7 degrees Celsius. So adding that 115 degrees zinc only raised the temperature of my water 0.7 degrees because it had a low specific heat and not very much of it. What I would do is to try questions 7 through 10 on page 284, the practice problems. The answers are in the back of the book, so you can see if you did them right. We'll see you tomorrow.